My name is Teddy and I'm a doctoral student whose area of research is logic. Obviously, I would like to know more about the world, so I decided to start a podcast where I invite mathematicians, physicists, philosophers, psychologists, and a lot of fascinating people who are willing to discuss with me interesting aspects of their work. I'm very excited about my first guest, the Oxford mathematician Professor Joel David Hamkins, a leading figure in the fields of set theory and mathematical logic more generally. You might also be surprised to hear that he is the top-rated user on the famous mathematical platform MathOverflow. We cover a lot of ground. We discuss notions such as infinity and the incompleteness of arithmetic. Some of this topic might be a bit mathematically demanding, but don't be put off by that. Just look in the description of the video for the timestamps. You are sure to find something that might interest you in there. So let's kick it off. So hello, Professor Hamkins. It's good to have you here.
Oh, it's a pleasure to be here.
So you are one of the highest rated users on Math Stack Overflow. What keeps you motivated to engage with mathematical enthusiasts all over the world?
Oh, I see. Well, actually, so I'm on MathOverflow, which is different from Stack Overflow, but MathOverflow is the mathematics version. And also there's another mathematics site with Stack Exchange called math.stackexchange. So I've been doing that for about 10 years, and really it's been such a great pleasure. I never dreamed that I would rise to be the top user, but I've been the top user there now for about 10 years. And it's just amazing to me. So when I first started doing it, one of my colleagues had pointed out the site to me, saying, look, anybody in the world can ask any math question that they want, and then people will answer it. And the level of questions is very high. They try to keep it at sort of research level questions, sort of graduate student level and higher. And so there's so many interesting questions there. You can just find all kinds of questions, whatever math question you might have, and also you can ask or answer them. And I just got sucked right into that, and it became an enormous time sink. In fact, I told my friend when he showed me, I just played around with it for a few minutes even, and I said, this is going to take an enormous amount of time. And it absolutely did. But what a pleasure it's been, really. I've just enjoyed it so much.
I've also checked you out on Twitter. You're quite active on there also. And I've seen that you're writing a new book, Proof
right.
and the Art of Mathematics. Can you tell us about that?
Yeah, so Proof in the Art of Mathematics is going to be coming out soon. It's with MIT Press. And this is a book which is about, it's aimed at aspiring mathematicians who want to learn how to write proofs. So basically undergraduate level. And what I've done is selected some of the most beautiful, compelling mathematical statements that I know that have elementary proofs. And I have about maybe 100 or 150 proofs in the book. And I discuss how to make a proof and how to go about writing a proof and how to approach the problem of proving a mathematical statement in the context of these different topics that are treated. So it's not all in one topic. There's a little bit of graph theory, a little bit about infinity, a little bit of real analysis, a little bit of geometry, and some lattice tiling problems and things like this. So I'm really hopeful. Actually, I taught in New York before I came to Oxford. I taught out of the draft copies of this book, and I felt it went really quite well. So I'm quite excited that the book is going to be available soon. Proof and the Art of Mathematics.
Yeah, it seems like you cover a lot of ground.
I try to. I don't know. I just try to do whatever I'm interested in. Actually, I have a second book that's coming out with MIT Press, a little bit behind. I mean, a little bit behind that one. And this is a philosophy book, so the lectures on the philosophy of mathematics. So this is the book that I wrote, and which I lectured from in my philosophy of mathematics lectures here at the University of Oxford. And so look for that one also. It'll be coming out soon.
I will. Speaking of, I don't know, mathematical students and mathematical education in general, I mean, people who haven't really delved into mathematics are a bit scared of it, and even adults. Some of them are even bragging about the lack of mathematical skills, which I haven't seen in a lot of fields. I mean, if you say that you are not good at music, as Hardy points out, people would not really appreciate that. But if you say that, I know, you're horrible at mathematics, people can relate to it and even encourage these sentiments. So why do you think mathematics is scary for a lot of people?
Well, I mean, I have complicated views on that question. I don't really think it's true that there is such a thing as a math person and non-math person. My view is that anyone can learn to appreciate and understand mathematical ideas. And I think that I could help people who have a kind of math phobia, I feel I can reach out to them, and it's about the choice of topic and how you explain a mathematical idea, and the I find it bizarre that it's socially acceptable to say that, that you find mathematics difficult. No one would say, "Oh, I don't like music," as you say, or I'm a person, or I'm not an ideas person, and so on. No one would say something like that at a party or something, and yet people say, "I'm not a math person" at a party. And I don't really understand why that's socially acceptable in a way, but also I think that it's a kind of that it isn't really true, that actually it's maybe they haven't had a chance to see the beauty actually that exists in mathematics, and if they had the right conversation, maybe they might change their view about that.
Right, let's talk about the subject more generally. I mean, mathematics seems to be different from the rest of the hard sciences like physics or chemistry. I mean, mathematicians seem to have a different modus operandi. They don't look out in the world to empirically confirm what they are investigating. So what do you think mathematics is? I mean, that's a broad question, and what sets it apart from the rest of the sciences?
Right. Well, it's really quite curious because mathematics is often grouped in with the sciences. I mean, at most universities, the math department is usually in the science division, and there's the whole concept of STEM subjects, which includes mathematics along with the sciences. And but as you say, it's not an empirical subject. We're not really looking out into the world. We don't find experimental validation of our theories. We search for proof, sort of a priori reasoning. In that sense, it has more in common with philosophy than it does with the sciences. I mean, in terms of the process of reasoning that one uses to make the truth claims in the subject. And so when you're putting me on the spot though about asking me to define what mathematics is, I'm not sure that I'm prepared to do that. Of course, I'm coming from the area of mathematical logic, and logic is concerned really with the role that often is concerned with the role that language has to play in helping us to understand or analyze or speak about the world, in the way that language expressions, including, say, a formal language or a mathematical language, can refer to objects. And then, of course, there's all kinds of philosophical problems, questions about what is the nature of mathematical existence of these objects. So how is this reference working? If I make a mathematical statement and it's referring to certain objects, then what are those objects really? And that's quite a difficult problem to give a clear account of what is the nature of mathematical existence. It's quite a difficult problem in my view.
Speaking of logic and language, I mean, Gödel, who is the father of modern logic, said that mathematics is discovered rather than invented. There are a lot of mathematicians who share this view. For instance, the Cambridge number theorist Hardy says the same thing. So where do you stand on this question?
Whether it's discovered or invented. So, I mean, of course, as a practicing mathematician, there's often different kinds of mathematics which play out in slightly different ways. And sometimes one has the sense that one is discovering something, and sometimes one has the sense that one is inventing something. If you're inventing new concepts, new mathematical ideas, and so on, then it has a more of a creative aspect to it. I mean, in terms of a practical, the way that it feels to do it. But if you're looking at a sort of well-established topic, some number theoretic question of whether there's a certain kind of number and so on, and you find one, then an instance of it, then obviously this is more of the character of discovery rather than invention. And so I can really see different kinds of mathematics exhibiting this distinction differently. And I don't think that there's going to be a uniform answer that applies to all of mathematics. It's not so homogeneous as that.
Right. So mathematics seems to be very useful for the sciences. I mean, theoretical physicists are able to predict the existence of the Higgs boson or gravitational waves way before their experimental colleagues are able to conduct experiments that really tell them, all right, we have found the Higgs boson. We have confirmed that there are such things as gravitational waves. But it comes as no surprise for the theoreticians, because they could already see it on paper. So this was dubbed the unreasonable effectiveness of mathematics. Why can mathematics be applied so beautifully to our universe? Why does the universe seem to operate according to computable functions and laws?
Well, that's an extremely difficult question. Of course, the indispensability of mathematics. I mean, the physicist Dirac, I think, said it quite beautifully that God is a mathematician of very high order. I mean, the sort of we see in the physical laws and that govern the physical universe, and how this mathematical nature to the physical universe, and why that should be instead of some other nature is really a deep mystery. But I want to point out something, which is that, so when, of course, a lot of times, a lot of the discussion in philosophy of mathematics is about the sort of ontological nature of mathematical objects. You know, what is a number really, and what are geometric structures really, and so on. And sort of, it's a question about the nature of the existence of these things and whether they do really exist, or is it all, can we eliminate those assumptions? Is it really dispensable or not? And people often have the view, it seems, that, well, in comparison with physical existence, which is totally clear, mathematical existence is thought to be uncertain and abstract. And I want to pour some cold water on that way of approaching it, because I don't think we do have such a clear idea about what it means to say that something exists physically. It's actually a fundamental mystery. I mean, when I knock on this table, what this table really exists, and it feels hard, and so on. But actually what it means to exist, I think, is a profound mystery. We can't really give a good understanding except by knocking on the table, and that's supposed to be the explanation of what it means to physically exist. But whereas we can give a pretty good account of what it means for, say, the empty set to exist, or the set containing the empty set to exist. I mean, you can tell a kind of story about the nature of abstract existence and what it means for such a simple set to exist in a way that's somehow more encompassing and fuller than it is, than any kind of explanation I can imagine about what it means for something physically to exist. You know, why should there be something rather than nothing? Well, there is something, but what does it mean to say that there's something, or that there is, you know, that these atoms exist physically? I don't think actually that we have a satisfactory account of that, just as we do not have really a satisfactory account of what it means to say that mathematical objects exist.
Speaking of sets, the whole field of set theory is sort of infused with the notion of infinity. Let's talk about this peculiar notion, because a lot of people seem to be interested in infinity. We might ponder a bit on its history and some of its paradoxical features that were resolved in the history of mathematics by figures such as Cantor. I don't know whether we should get back to Aristotle and Plato and the discussion about actual and potential infinities.
Well, of course, infinity goes way, way back. I mean, all the way to Aristotle and so on. And but really Cantor's amazing discovery that there are different sizes of infinity was really an incredible achievement. And it's interesting to notice that Galileo, sort of hundreds of years earlier, almost had it. He was so close. So, for example, Galileo had pointed out that if you take the numbers 1, 2, 3, 4, and so on, and you consider the squares, so the numbers 1, 4, 9, 16, 25, those are the perfect squares. Galileo noticed that, look, we can match them up. We can associate every natural number with its square. We can associate 2 with 4, and 3 with 9, and 4 with 16, and so on. And so, therefore, it seems like, Galileo said, that there are just as many numbers as there are perfect squares, because every number can be associated with its own square. But then again, on the other hand, it seems like there's many fewer perfect squares than there are numbers, because, you know, there's all the other numbers in between, and the gaps get bigger and bigger as you get as you go out. And so basically, Galileo had this idea of equinumerosity of sets. The numbers and the squares are equinumerous, but it seems, on the other hand, that there are fewer squares. And so Galileo's response was basically to throw his hands up in the air and say, therefore, we don't really understand infinity. But Cantor's approach to this issue was a bit different, and he doubled down on it. And he said, no, what we want to do is take this equinumerosity idea seriously. And that's what it means for two infinities, two sets of any size, finite or infinite, to have the same size if they can be put in one-to-one correspondence. So when I look out in a classroom full of people, then I know that there's a one-to-one correspondence between the people and the noses in the room, because every person has a nose and only one nose, and there aren't any spare noses in someone's pocket or something. And therefore, even without counting the number of people, I can tell that there are just as many people in the room as there are noses in the room because of that correspondence. And similarly in mathematics, when you have two sets, you can say that they have the same size when you can find a one-to-one correspondence between the elements of those sets. And there's a related idea, actually. So philosophers often talk about equinumerosity, but there's another. Really what we want is not just the notion of same size, but the comparative notion to say that one size is less than or equal to another. And Cantor does this also, right? So one set is less or equal another in size when there's an injection, when there's a one-to-one correspondence from this first set to a subset of the second one. So every element of the first set is corresponding to an element of the second one, but maybe you don't use up all the elements in the second one. So this is a notion of less or equal on sets for even infinite sets. And it's a very deep theorem. The Schroeder-Cantor-Bernstein theorem says that if you have two sets and each of them is less or equal the other, then they have the same size. It's not obvious. I mean, when you say it like that, look, if I have two sets and each of them is less or equal to the other, then they have the same size. It sounds like something we obviously want to be true, but you have to do some work to prove that with these notions, and it is true. It's a theorem that if you can inject a set one way and you can have an injection from the other set in the other way, then in fact those two sets can be put into bijective correspondence with a one-to-one correspondence.
Right, but so far we discussed sets such as the natural numbers and the squares of natural numbers, but these happen to have the same cardinality, and a lot of people are puzzled when you say that Cantor actually has a theorem that you can climb up sort of an infinity ladder.
Sure.
So can you tell us a bit about Cantor's discovery?
This, of course, is Cantor's famous theorem that the real numbers are uncountable, and so it's his diagonal argument, for example, that what he proved is that we have the infinity of the natural numbers, 0, 1, 2, 3, and so on. And then there's the infinity of the real numbers, if you think about the number line and all the points on the number line, or every real number, including the decimal numbers whose digits never stop, like pi and e and so on. Then if I take all the real numbers together, there is no one-to-one correspondence between the natural numbers and the real numbers. It's impossible. And the way Cantor proved this was by suppose that there were such a enumeration of the real numbers. If we could find a one-to-one correspondence between the natural numbers and the real numbers, then we could basically make a list of all the real numbers. And what Cantor proved then was that for any such list of real numbers, there's a first number on the list, a next number, a next number, a next number, a next number, and so on. Then for any such list, we can write down another real number, the digits of another real number, and prove that this new number is not on the list. And therefore, it's impossible to have a list that contains all the real numbers. And it's really an ingenious argument that he gave. So what we do is we make a real number, the new real number, and we make sure that the first digit after the decimal point is different from the first digit of the first number. And we make sure that the second digit after the decimal point in our number is different from the second digit of the second number. And the third digit should be different from the third digit of the third number, and so on. So what we're really doing is working on the kind of diagonal of the digits. We make the nth digit of our number different from the nth digit of the nth number on the list.
Yeah, so
of course, is that this number that we can describe is not equal to any of the numbers on the list, because it's different from the nth number in the nth place. So it's really an ingenious argument, this diagonal argument. And actually, it's such a powerful argument tool that it appears now in thousands of different arguments. So some people say that every single proof in logic, in mathematical logic, uses the diagonalization method at heart. So it's such a fundamental way of arguing that it has hundreds and hundreds or even thousands of applications.
But his theorem actually goes a bit deeper than that. I mean, it actually says that whenever you have a set, if you consider this set and the set of its subsets, you actually put your finger on a set of a higher cardinality. So in a way, starting with the natural numbers, you then get the power set of the natural numbers, and then you get the power set of the power set of natural numbers. And each of these sets give rise to a sequence of different infinite cardinalities, if you consider their size. So in a way, I'm not sure whether we shed some light on the notion of infinity, but on the other hand, mathematical amateur might think that it has the same flavor as the natural numbers after all, because we still get things in sizes in sort of a discrete way. Yeah, what do you think about that?
Well, of course, that's completely right what you said. I mean, describing what Cantor had proved. It's interesting to ask. I mean, so you said, well, let's take the natural numbers and then the power set. That's the same size as the real numbers, so the power set of the power set is bigger still, and so on. Sometimes people say, I mean, there's a kind of easier way to understand the claim that the set of all subsets of a set is strictly larger than the set. If you take any set of people and consider the collection of all possible committees that you could form from those people, then there are strictly more committees of people than there are people. They cannot be put into one-to-one correspondence even when there are infinitely many people, which is another way of saying that, that the power set of a set is bigger. So far though, you've only got countably many different infinities, right? So you have the natural numbers in its power set, and its power set, and its power set, and so on. And that gives you countably many different infinities. So one could ask, well, how many different infinities are there? And of course, if you could make a set that was somehow on top of all the ones that you just described, like by taking the union of those sets, and in order to prove that that set exists, you need what's called the replacement axiom. So actually in Zermelo's original axiomatization, you couldn't prove that there were more than countably many infinities. But with the Zermelo-Frankel axioms, then you do have the replacement axiom, and so you can prove that there's a set on top of all of those. And then that set is bigger than any one of them, and then you can take its power set, and its power set, and its power set, and so on, and you get another kind of limit, and then you want to get an infinity on top of that, and so on. And so it turns out to be a mathematical theorem that for any given infinity, there are more than that number of infinities. So the number of infinities, well, it's not really correct to talk about the number of infinities because there is no such number, because it's bigger than any given infinity. So then the question is, well, is it like the natural numbers again? And I think if you have this kind of transfinite iteration picture, then it starts to look much less like the natural numbers, because there are these limit stages, and then limits of limits, and limits of limits of limits, and so on. And it really becomes quite complicated as you go up. And eventually you get up to what, for example, the Hausdorff had introduced, the inaccessible cardinals. This gets into the large cardinal hierarchy. So it's a concept of infinity which is so large so that, well, first of all, it's uncountable. And secondly, for any smaller infinity below it, its power set is also still below it. So it's somehow closed under this operation that you were just talking about of taking the power set. But also, an inaccessible cardinal has the property that there's no short ladder that climbs all the way up. So any ladder of length less than the given cardinal is bounded below the cardinal. This is called regularity. And these inaccessible cardinals, they appeared in the earliest days of set theory, really quite fascinating, and grew then eventually into what's now called the large cardinal hierarchy. We have dozens of different kinds of these extremely strong axioms of infinity. We can't prove that there's an inaccessible cardinal, although most set theorists believe that it's consistent with the axioms that there are these inaccessible cardinals, or maybe they even believe that it's true that there are inaccessible cardinals, even though we can't.
I'm afraid a lot of people might be scared of what the inaccessible cardinals might mean if they have never done a set theory course. But speaking of the set theory axiomatizations, I mean, let's talk about another important moment in the history of this branch of mathematics. The notion of infinity infected set theory at some point in the past, and that was clearly expressed by Russell's paradox. Can you please tell us what Russell's paradox is and what effect it had on the history of maths?
Sure. So there's a kind of naive idea when you approach set theory naively, then it seems like one of the most fundamental operations that you're doing is that for any property, you can form this set of all x, the set of all objects x that have that property. That seems to be what's going on with set formation. When you first come to set theory, it seems like, well, if you have a property, you can pick out the collection of all objects that have that property. And what Russell proved, well, actually, it was in response to Frege's work. So Frege had taken this principle as a fundamental principle in his in the Grundgesetze and built an enormous edifice, this mathematical development on top, basically, of that principle. And Russell observed that actually that principle is just wrong. It's inconsistent. It's self-contradictory by a very easy argument. And the Russell argument is like this. Well, consider the property of not being a member of itself. So Russell said, let's take the set of all x such that x is not an element of x. Now that's a very ordinary property. Most sets have the property. For example, the set of all elephants is not an elephant. It's a set of elephants. So the set of all elements is not a member of itself because it isn't even an elephant at all. Or the set of all people in this room is not a person in the room. It's the set of people in the room. And so it's not an element of itself. Or in most sets that you might write down, the set of all even numbers is not an even number. So it's not an element of itself either. So it's really quite ordinary to be non-self-membered. And Russell said, well, let R be the set of all non-self-membered sets. And now he asks, is R a member of itself or not? And if it is, then R would be self-membered, and so it shouldn't be an element of itself in that case. And if it isn't an element of itself, then R is non-self-membered, and so it should be an element of itself. So basically, Russell derived a contradiction just from defining this set. Let R be the set of all non-self-membered sets, and then R is an element of R if and only if it isn't, and that's a contradiction. So it shows that axiom is just wrong, and we can't allow it as a fundamental principle in set theory. And so the axioms of set theory as they're treated today don't have that principle. And a kind of a little more sophisticated way to approach it is to look at, well, what is your picture of the set theoretic universe? How are sets built up? Well, we have the idea that, well, maybe there's a bunch of mathematical objects which aren't sets, and we're going to use them to build sets. You don't actually need anything in set theory. You can start with nothing. But it's also common to start with some elements or sort of primitive objects, mathematical objects. And then at the next level up, you have the sets of those kind of objects. And at the next level up from that, you have the sets of those objects or sets. And then at the next level up from that, you allow sets of the things that you already created. So there's this cumulative universe that's growing, this cumulative hierarchy of sets. That this is how sets come into existence. First, their elements have to come into existence, and then you form the sets of them, of those elements. And if you have this picture of how sets are forming and into a cumulative universe, then there's no support for the general comprehension principle, the principle that we were talking about before, because maybe sets are appearing at every stage in the whole hierarchy, but for example, we would never get the set of all sets because that wouldn't appear at any stage in the hierarchy because all of its elements would have to have already appeared. And so if we contemplate about what we think the nature of set theory is like, then it has this kind of well-founded hierarchy, this cumulative hierarchy aspect to it. And when you have that picture of set formation, then the attractiveness of general comprehension simply falls completely away, and you recognize that it's a naive principle, which is very easily proven wrong.
And this existence of paradoxes in the set theoretical branch scared famously David Hilbert in the 1920s, or perhaps even earlier than that, but that's when is that when the Hilbert program started, in the 1920s?
Yeah, well, it's one of the principal motivations for the Hilbert program because,
right.
I mean, what Hilbert looked at what was happening in mathematics, and there were these kind of new foundations coming. I mean, these set-theoretic foundations that were being developed in Cantor's ideas about infinity, and Hilbert famously said, "No one will cast us from the paradise that Cantor has created for us," because he saw this sort of set-theoretic way of thinking about the nature of mathematical objects was such a powerful foundational method. He didn't want to give it up. But these kind of paradoxical arguments that kept coming up, such as the Russell paradox and others, were worrisome because people didn't really understand what was going on and what should be the correct axioms, and could we know that they're safe. And so what Hilbert wanted to do was, well, it's really sort of two prongs. What he wanted was, he wanted an axiomatization of mathematics which would answer every question. So he wanted a complete axiomatization of mathematics. So he wanted a mathematical theory, perhaps set theory or some theory like that, which would answer every mathematical question. And then secondly, he wanted to be able to prove, it was fun for him for that theory to involve infinitary notions like set theory and so on, but in order to really secure the utility of this theory, he wanted also to prove by purely finitary means that this theory was consistent. So he wanted a good theory that would answer all the questions, and he also wanted to prove that that theory was consistent, where the consistency proof would appeal to only finitary mathematical principles about which we had no doubt.
So why was he so comfortable with finitary mathematics? I mean, what is finitary mathematics?
Well, okay, this is a difficult question to really say exactly what it means and what he meant by it. But of course, I think it's quite natural, given what he's trying to do, if you have some worry about set theory, which he did and which many people had at that time because of those paradoxes, then it would obviously be comforting to prove that your theory is consistent without using those outlandish infinitary means, or committing yourself to those infinitary mathematical objects. And so, but one way of interpreting it is, basically at that time there were various axiomatizations of arithmetic circulating. For example, the piano axioms, which Hilbert thought of, maybe it was going to be the right basis for founding mathematics and for undertaking the finitary argument, would be just the piano axioms of arithmetic. So really, though, of course, the whole Hilbert program was completely and decisively refuted by Gödel's incompleteness theorem. I mean, both parts of the Hilbert program were just decisively refuted. It's interesting to think, actually, if you imagine what it would be like to live in Hilbert's world. Suppose that Hilbert had been right. Suppose that we could write down a theory and then prove by finitary means that it was consistent. But just think about that, that complete theory. So we could write down axioms of mathematics which would answer every question. What would mathematics be like in that situation? Well, if you had a complete theory in mathematics, then what you could do is just start systematically proving theorems from this theory. You could every day just prove the next theorem. You could automate theorem proving, and furthermore, this procedure would work perfectly, because if the theory was complete, then it would prove every statement or its negation. So if you had a mathematical question, then you could undertake the following procedure. You just start turning the theorem proving crank. You just turn the crank. You prove everything that's possible systematically. And then eventually either this question or the negation of the question will show up as one of the theorems. And so if Hilbert had been right, then the nature of mathematical activity would become this kind of, it would have a nature of automaticity, and because in principle one could answer by a computable procedure any given mathematical question. Whereas if Hilbert is wrong, which Gödel eventually showed that he was, then the nature of mathematical reality would be that, well, we could have some axioms, but they would be incomplete, so they wouldn't settle every question. So there would always be questions that we couldn't answer. And secondly, we would always have some kind of doubt about whether we had the right theory or even about whether it was consistent. And Gödel's theorem shows that, in fact, that's the true state of affairs. We can't really be certain of the consistency of our mathematical axioms. And furthermore, for any of our mathematical theories, there will always be questions that those theories aren't able to answer.
Let us ponder a bit about what Gödel's theorems actually say, because I guess a lot of people don't really understand what they state. I guess we can focus on one particular system of axioms, like the piano axioms that you mentioned. So we have this thought in our head that there is a natural number structure. We start with 0 and we apply a successor to each element. And then we state out precisely in formal terms what we think is obvious concerning this structure. So it starts with a 0. So I guess 0 is not a successor. If I have two successors that are equal, then sort of their arguments are equal. And two axioms characterizing additions and multiplication, and the principle of mathematical induction. And the thought is that whatever satisfies these axioms deserves to be called the natural numbers. And also we precisify what we do when we do mathematical proofs. So we allow very strict rules like modus ponens. So if we have P implies Q and P, we can derive Q. And those things have to be very carefully mechanized so that there would be no gaps in our proofs. So there's no place for informality. And I guess what Gödel showed was that in this very strict system, we cannot put our hands on with a proof on all mathematical truths. I mean, we can cook up a certain mathematical statement, which is not able to be derived within the rules of the game. And more or less, it's an incompletability theorem, because even if we add that statement to our set of axioms, we would still have an incomplete system, a new one. So I guess that differs in a way with the standard mathematical methodology. I mean, mathematicians don't typically write very rigorous formal proofs. Do you think there's any fundamental difference between the way mathematicians do mathematics and the sort of Hilbert style proofs that are dealt with by Gödel?
So yeah, everything you said about the incompleteness theorem seems to be completely right. So of course, underlying the idea of the incompleteness theorem is the need to have a formal proof system, which is what Gödel had provided in his doctoral dissertation, the completeness theorem. So he defined what it means to prove a statement. I mean, I think before that time, people weren't so clear on the difference between asserting that a statement is true and asserting that a statement is provable. And Gödel really, we have to distinguish between these two notions, between mathematical truth and mathematical proof. And one does this by defining some formal proof system of the kind that you're just describing with modus ponens and so on. And one interesting thing that I like to mention when I'm talking about this kind of the completeness of the proof system. So Gödel proved that if you have a theory, if you have a first order theory to which his proof system is amenable, then the provable statements from the theory are exactly the same as the valid statements in the theory. And valid means that a statement that holds in all models of the theory. So a theory proves a statement if and only if the statement is true in all models of the theory. Now, one of those directions is very easy to see. Of course, if you can prove it, then it must be true in all models, because your proof system is sound and the rules of the proof system are truth preserving. So that's very easy to see. But the profound part of that is that if a statement, say in arithmetic or in graph theory or group theory or whatever mathematical theory you're talking about, is true, say I have a statement in graph theory and it's true in all graphs, then there's a proof of it from the axioms of graph theory, which are very minimal. And that is amazing and profound, because being true in all models of the theory has to do with these possibly uncountable models, or this sort of huge number of different models in which that theory is true. And it just happens that you have this sentence that's true in all of those different models. And why should that kind of metaphysical fact that the statement happens to be true in all the models of your theory mean that there's this finitary combinatorial object, which is the proof, the formal proof of the kind that you were talking about? obeying modus ponens and so on. And it's quite difficult to see at first where this proof is going to come from. So I assume I've got a statement, say sigma, and it's true in all groups, say, then how am I supposed to find the proof of sigma from group theory? But the fact of the matter is that that's what Gödel did. He proved that there is a proof. And what it means, the way I interpret this statement, is that there are no accidental mathematical truths. Every mathematical truth is true for a reason. Namely, if something is true in all models of the theory T, then it's true for a reason, and the reason is the proof. The proof is showing us exactly why it's true. And so this is a way of saying, if everything that's true in all models of the theory has a reason why it's true, then there can't be accidental truth. It can't be that something just happens by accident to be true in all the models of the theory. So I'm not sure I answered your question, but I wanted to mention that aspect of proof. So you were asking about sort of the nature of formal proof or the value of it, and it's really important and timely, because now with the increasing computer power, it seems inevitable that we're going to have extremely powerful automated theorem proving capabilities. And many mathematicians are getting behind this effort to build more and stronger and better automated theorem provers. And of course, these automated theorem provers are of course using these formal systems to find proofs. And I think, I mean, listening to some of the people talk about it, there's this vision of the future that basically all mathematicians are going to be using formal proofs, on their computer, and all mathematical claims will be validated by these formal means, whereas currently they aren't. I mean, of course, the kind of naive perception of the nature of mathematical claims in the mathematical research literature is that if you prove a theorem and it's published in a journal, then it's rock solid 100%. But of course, this isn't true, and all these mistakes happen, and theorems are published that actually turn out later not to be correct, and so on. And so the automated theorem proving and the sort of proof checkers are meant to kind of put an end to that kind of thing by all mathematicians would use these computational methods to validate proofs by these formal means, and so we could really be completely sure of the truth of the result. But my personal opinion is that that's not how it's going to be. It won't be that all mathematicians are doing this. This is going to be a particular area of mathematics, and the experts in formalization will be working with these systems, formalizing the mathematics of other people. It won't be that everyone is validating their own theorems, because it's a skill to formalize the mathematics, and oftentimes the things that are involved in the formalization are not exactly the same as the mathematical insights and ideas and concepts that need to be used in order to think of the subject. And so my view of the future is that there will be a huge body of people who are validating other people's theorems and theorems coming from other parts of mathematics, but there will always be a place for what I view as this sort of true mathematical insight, and that we don't really want a formal proof of our theorem. If I prove a theorem and I have a proof and so on, and I can explain it to someone, and then at the end of the proof they say, aha, now I see, I get it. And that is the aha moment, is the sort of mathematical insight is really what we're after. I don't want to just know that something is true. I want to understand why it's true, and I'm not going to get that extra bit from the formal proof at all. The sort of epistemic added value of those formal proofs is very low, very, very low. I mean, once you know that the thing is true because you have a proof, the formal proof really convinces you, yeah, you haven't made a mistake, it really is true. But you're never going to get these mathematical insights from the formal proof. Those are going to come from the sort of human level explanations and understanding that the mathematicians are already providing.
And there's another notable features of these formal proofs and automated proofs, namely that they are sort of ugly. Some of them might just run through case by case in a way that humans would not be able to do. So at least me, perhaps other people have this feeling as well, it would kill the artistic aspect of mathematics if we would rely solely on automated provers. So I wanted to ask you, a lot of my mathematical friends say that when they do mathematics, they feel like they they are engaging in an art form. And you also have in your book title the word art. Do you think that using computers to do mathematics would kill this noble art?
Well, I mean, of course. Well, I want to rebut a little bit what you said, because people are addressing this question of whether the proof checkers are necessarily so distant from mathematical practice. And the sort of the latest effort, if you look at, say, homotopy type theory, it's being proposed explicitly as something that is much closer connected to how mathematicians are thinking and working. And so the claims that are being made about homotopy type theory is that it is much closer in such a way that it is possible to imagine that mathematicians would be using this every day. I don't think that that's true. I don't think it's fully true, but I wouldn't be as extreme as what you had said. But about art and mathematics, of course, I mean.
Also, before you answer the question, perhaps
Sure.
you might also spell out what you take to be the artistic qualities of a beautiful mathematical proof. Andrew Wiles, when he famously proved the Fermat's last theorem, he says in an interview that it was the most beautiful moment of his life. So a lot of people have this feeling that they are engaging in a very intellectually satisfying art form when they finally crack the mystery of a proof. So what would you say that are the artistic traits of a proof? And I guess that would also help you answer my initial question.
Right. Well, I mean, of course, I don't have any, sweeping account of what art and mathematics is about and so on. All I know is what the kind of mathematical arguments that I enjoy and that I strive. I mean, this aha moment experience is really so profound when you struggle with a mathematical question and you struggle and you think about it and you're banging your head against the wall, not being able to answer, and then it happens that suddenly you think about it in a certain way and you realize, oh my gosh, really everything is just fitting together perfectly. It all just comes together and you say, aha, it's amazing. And your mathematical gaze is able to just pierce completely through in a moment. And this is such an incredible feeling of you understand something so deep and vast all at once, and that's such a great feeling. And this is, I think, connected. It maybe that way of talking about it isn't so much about art, but really I think this the explanations that serve that purpose, that lead you to that state, I think are the same ones that people say are beautiful and elegant, because they inspire this feeling in you. Maybe it's comparable to the feeling that you might have of understanding something about the nature of human existence, looking at a profound photograph or artwork of some kind. And so maybe that's the sense of art that people talk about. It might be something like that. But then again, one also has to, maybe pour a little cold water on the whole aha moment thing. My wife sometimes says, yeah, Joel has these aha moments. He'll say, aha, I've got it. And then, 10 minutes later, it's, oh, wait, well, and of course, the arguments break. And so there's these kind of fake aha moments where you think you understand something, but actually you don't, because it turns out to be wrong. And then you wait and you get another one, and then that one's wrong, and so on. And this is maybe a little more realistic description of the nature of mathematical development. So I don't know how that relates to art so much, except that, maybe it would be like looking at a painting and thinking that you understood something deep about the nature of human existence, and then realizing later that actually that the insight that you thought you had wasn't quite right.
Speaking of computers, I mean, I might backtrack a bit in the history of computability to
Sure.
Precisely 1936, when the British mathematician and logician Alan Turing published the Uncomputable Numbers with an application to the Entscheidungsproblem paper, where he basically answered the question of what is computation by providing a rigorous model of computation, the famous Turing machine, where computation would be defined a step that is performed by this abstract mathematical object. So you worked a bit on this, and it's fair to say for the viewers that everything that modern computers do can be done by a Turing machine. Just describe, what do you do when you talk about infinite time Turing machines? Do you Do you only deal with the tape or with the number of
Sure. The
steps?
first model, I mean, the infinite time Turing machine model, it doesn't extend the tape. Actually, the hardware is identical to a Turing machine. So our idea was to extend the operation of the machine into infinite time rather than infinite space. Although now we have many other models, and in some of the models, they did extend the tape as well. So various other people are working on this, including Peter Kopke and Bond. So the infinite time Turing machines is the original model, had the same hardware as an ordinary Turing machine, but what we wanted to grapple with was the idea that, well, you could set a Turing machine running and maybe it wouldn't ever halt. So the head is moving back and forth on the tape as you described, and maybe it's writing more and more information out on the tape. For example, maybe it's writing all of the Fermat primes that it finds on the tape, or maybe it's writing out all the theorems of mathematics on the tape and so on. So we can easily design machines that do quite amazing things without halting, and somehow the information that they're putting on the tape could be quite interesting. And so what we wanted to do was define a kind of limit configuration and that enabled the machine to continue after having filled up the tape. So we say at time omega, in other words, the time steps go 0, 1, 2, and so on. So as the head is moving around, and then at the limit time, at time omega, the head might have been racing off to one end, or maybe it had come back infinitely often, and somehow whatever the behavior was, we put it on the first cell, on the start cell, and we put it in a special limit state, and then we update each cell on the tape with the limit of the values that had appeared in that cell, or actually we take the lim sup. So if it had stabilized at 0 from some point on, then we leave it 0, and otherwise if it had alternated 0, 1, and so on, or if it had been 1 from some point on, then we leave a 1 in that cell. So then at the limit state, we have a complete configuration of the machine. We know where the head is, we know what the state is, and we know what's on the tape. And we can let it continue computing to time omega plus 1, omega plus 2, omega plus 3, and so on. And then, of course, we get up to omega times 2, and then omega times 3, and so on. And so we go through all the ordinals with time, not with space. So it's infinite time Turing machine. And we analyzed, so Jeff Kidder and Andy Lewis and I analyzed the power of this, the theoretical power of this model of computability. Of course, you couldn't really ever build one and run it because of this infinitary nature. The problem was it wasn't a model of a kind of practical computing method. It's a kind of theoretical model of what would be the power of these machines if we could actually run them and use them. And so we analyzed this in the context of maybe descriptive set theory, which is the field of mathematics that's about sort of complexity of sets of real numbers, and that's really the right domain to analyze it.
Right, but even in theory, are there interesting mathematical problems that are widely known that would be able to solve with these new computational resources that your infinite time Turing machine provides? I mean, can you, for instance, crack Goldbach's conjecture by allowing to search with infinite time for a Cantor example, or I don't know?
Yes, you absolutely can. I mean, in fact, what we proved is that for any number theoretic question, including Goldbach's conjecture, the Riemann hypothesis, or these classical number theoretic questions, all of them can in principle be solved by these infinite time Turing machines. In fact, you don't even need, for those two, you don't even need more than one limit. You only need to go through one limit and then a few steps more, and you can answer those questions. But in principle, for any number theoretic assertion, you can always answer them in time less than omega squared. You never need infinitely many limits, only finitely many. But of course, the machines are much more powerful than that even, and so we push into what's called the delta 1-2 level of descriptive set theory. So this includes all of the first order arithmetic assertions, but also we can even answer questions that use one quantifier over the real numbers. So we can answer questions of the form, is there a real number such that we don't search for the real number and find it. That's not how the algorithm works. But in principle, those questions can be answered and the witness can be provided.
You mentioned before that the question of whether mathematics is discovered rather than invented depends on the subject area that you're discussing. So let's consider something more particular, take arithmetic or number theory. Do you think that numbers inhabit a determinate mathematical reality where every answer is settled and the job of the mathematician is just to discover truths that obtain in that particular reality?
It's an absolutely great question. I mean, this is kind of the kind of question I was referring to about what is the nature of mathematical existence. And many mathematicians and philosophers of mathematics have the view that arithmetic in particular exhibits this character of definite truth in a way that, I mean, much more strongly than other parts of mathematics, say in set theory or in analysis and so on, the sort of higher realms. And there's this view that many mathematicians have that arithmetic assertions about, about the nature of the natural numbers have definite answers. And I feel that pull of that view, but I'm a little bit hesitant to adopt it wholesale because, of course, because of the incompleteness phenomenon identified by Gödel, we know that we can't identify a complete theory of arithmetic truth. So whatever theory that we're putting forward is always going to be incomplete and inadequate and leave things out and so on. And this is a fundamental feature of the nature of mathematical reality, that there's always going to be this sort of uncertainty and incompleteness about our knowledge about the subject. But I push this a bit farther, and I wonder whether even we do have a definite concept of natural number. I mean, there's this idea, okay, the natural numbers, they start 0, 1, 2, 3, and so on. But and people have this vision of maybe the telephone poles, receding into the distance one after the other, and everyone has the next one and so on. And but is that really a basis for such strongly held view that all arithmetic assertions have a definite truth value? I don't think so. This and so on is just much too vague to really allow it to do so much work. So other mathematicians and philosophers point to, say, the Dedekind categoricity argument. So this is the proof by Dedekind that there's a unique natural numbers structure which has a 0 and a successor, and in which 0 is not a successor of any number, and the successor operation, I mean, the adding 1 operation is a one-to-one operation. And furthermore, every set of natural numbers that contains 0 and is closed under the successor operation would contain all the numbers. That's the second order induction axiom. And so what Dedekind proved is that there's only one such structure. It's the natural numbers structure. Up to isomorphism, if you think you have two of these structures, then really they're isomorphic. And so the idea is that the Dedekind categoricity argument shows us that when it comes to the natural numbers, we know what we're talking about. There's only one structure. But my kind of criticism of this view, I mean, in terms of establishing the definiteness of arithmetic, I think it's a complete failure in doing that because it's a second order exponentization. So the point is that in order to understand what we mean by the natural numbers, I mean the numbers 0, 1, 2, 3, and so on, we have to already know what we mean by an arbitrary set of natural numbers, because that's the second order induction axiom. And so how could we possibly secure the definiteness of natural numbers by appealing to this comparatively vague idea of arbitrary set? So I don't see that can be a successful answer to the question of whether there is a definite singular nature to the natural numbers. And so I wonder whether we really do have such a clear idea about what it means to be a finite number. We already know, because of non-standard analysis and so on, we already understand quite deeply how it could be that there are other non-standard number systems that satisfy all exactly the same truths as the standard model, and yet themselves are not standard. So we know that can happen, and we know in a quite deep way how you can have different non-isomorphic models that satisfy all the same first order truths, and even first order truths in set theory, which would then give their own separate account for the second order induction axiom of Dedekind. And so we already understand in a quite deep way how it could be how there could be a sort of coherent mathematical universe with its own different conception of the natural numbers, which was not the same in this universe as in this one over here, and so on. And there's a whole kind of spectrum of different mathematical universes that would each provide their own concept of natural numbers, and that those concepts wouldn't be the same. And how do we know that this idea 0, 1, 2, 3, and so on is really picking out a unique one when we already understand how it could be that there are these diverse different models?
It crossed my mind, and I feel like it's worth asking you about this. Cantor left one problem undecided. I mean, we mentioned the fact that the set of natural numbers and the set of the squares can be put in the one-to-one correspondence. We also saw that the natural numbers cannot be placed in a one-to-one correspondence with the real numbers, because they can't even be placed into one-to-one correspondence with the numbers between 0 and 1. But Cantor asked whether we have a set of intermediate cardinality between these two. The rationals wouldn't count, because surprisingly, the naturals can be placed in the one-to-one correspondence with the naturals and the rationals. So what do you think is the answer to the question of whether there exists such a set of intermediate size between the naturals and the reals?
Well, I mean, of course, this is the famous continuum hypothesis, right? So the continuum hypothesis asserts that there isn't any infinity in between the natural numbers and the real numbers. And Cantor struggled with this question for his whole life. And it was unresolved for decades even after that. So Gödel proved in 1938 that it's consistent with the other axioms of set theory that the continuum hypothesis is true. And then in 1962, Cohen invented the method of forcing and used it to prove that it's also consistent with the other axioms of set theory, that the negation of the continuum hypothesis is true. Or in other words, that CH is false. And so this is what it means for the statement to be independent. The continuum hypothesis is independent of the other axioms of set theory. You can't prove it, and you can't prove that it's not true. So it's neither provable nor refutable. And now we have really hundreds, thousands of instances of this kind of independence phenomenon. It's completely pervasive in set theory. The main lesson of 20th century set theory, the latter part of the 20th century set theory, is the pervasive independence phenomenon. Almost every interesting set theoretic question turns out to be independent of the axioms of
do you have another one that is easier to understand at hand?
Well, easier, let's see. I mean, basically any question about cardinal arithmetic. So the continuum hypothesis is asserting that the power set of the natural numbers has the same size as the next infinity after the natural numbers, so as omega 1. I mean, and you could ask other questions. What about the power set of omega 1? Is that the same size as Aleph 2, or are they different? So Lucen had a competing hypothesis, which is he thought there should be exactly one infinity. I'm sorry, I haven't said it right. Lucen's hypothesis is the assertion that the power set of the natural numbers is equal to the power set of Aleph 1. So in particular, they have to both be bigger than Aleph 1. So it implies the negation of CH. But this statement also is independent. Then there's principles, well, the diamond principle, the question about Suslin trees, Suslin lines. Oh, okay, so maybe we could mention that. Suslin looked at the hypothesis. So one of the characterizations of the real number line is that it has a countable dense set. It's a dense linear order without endpoints. So meaning between any two real numbers there's another one. And it has a countable dense set. So it's a and it has the Dedekind completeness property. So it's a complete linear order which is endless and dense, and it has a countable dense set. And any such order is isomorphic to the real number line. You can prove this is a characterization of the real number line. And what Suslin was interested in was the question, well, suppose we replace this assumption about having a countable dense set, the rationals, and we just say for every family of pairwise disjoint intervals, there's only countably many. So in other words, you can't have an uncountable family of pairwise disjoint intervals. But that's true. If there's a countable dense set, then every such interval in that family would have to have one of the elements from the countable dense set. So there could be only countably many in the family. But it's not so clear how to argue the other way. And so Suslin asked, is it still true that the reals are the only such line, which is a complete linear order, a complete dense linear order that has this chain condition property that every family of pairwise disjoint intervals is countable? And the answer turns out to be extremely interesting because it's independent of the axioms of set theory, making certain consistency assumption, and it's just fascinating to think. And really, this is part of the kind of contemporary set theoretic perspective on the nature of the real number line. If you don't have an axiom that tells you whether or not Suslin's hypothesis is true or not, then what is the true state of affairs? So if you think that there's a kind of definite nature to the real number line, and that there's a fact of the matter about whether or not it's characterized by that property or not, then you're gonna maybe have a problem thinking about how it is that you're going to come to know those facts about the real number line, given this pervasive independence phenomenon. There's all kinds of questions about the real numbers that are independent and that are not settled by the axiom. So how do we decide what axioms to add? We have all these independent statements. We can add some of them are inconsistent with each other. We can have this one or that one, but not both, or we can have the negation of this one and so on. So we have all these different axioms. I mean, dozens, hundreds of different axioms, and we don't know the procedure by which we should be adopting them, or if it makes sense. So as set theory developed, it became more and more about proving consistency assertions about different combinations of these axioms. So you want to have CH fail, but you want to have this other feature and so on. And so what a lot of the work that set theorists are doing is proving and constructing mathematical worlds or set theoretic universes in which certain combinations of set theoretic axioms are exhibited. And when you have a lot of experience with these kind of arguments, then the whole subject seems to become about there's all these different set theoretic worlds, and any one of them could serve as a foundation of mathematics in the sense that set theory can serve as a foundation of mathematics. But the nature of those of mathematical truth in those different set theoretic worlds is different in the different worlds. And for example, in some of them, the Suslin characterization of the real line works, and in other ones, it doesn't work. And so the nature of mathematical truth is divergent between these different mathematical worlds. And set theorists have become quite used to jumping from world to world and building these different set theoretic universes from others and from each other. And so this led me to think that actually to develop my ideas about the set theoretic multiverse, and the idea that really there are different concepts of set that correspond to these different set theoretic worlds, and all of these, the independence phenomenon is giving us evidence in favor that there's a kind of plethora of different set theoretic concepts, different concepts of set, and these different concepts of set give rise to different mathematical foundations which exhibit different mathematical truth. I mean, one can, for example, make an analogy with what happened in geometry, a little over a century ago. Well, for thousands of years, we had the subject of geometry that was developing, and mathematicians and geometers generally had the idea that what the subject was about was geometry, and there was one subject of geometry, and they were doing geometry by studying and proving theorems from Euclid's axioms and so on, and the subject of geometry was about the one through geometry. But with the discovery of non-Euclidean geometry, it shattered that view, and mathematicians realized that there are different concepts of geometry. There's different ways that we can think about points and lines and planes and spheres and so on existing, and the mathematical facts of the matters are different for these different concepts. Sort of hyperbolic space just has different geometrical facts in it than spherical geometry or Euclidean plane geometry. or in any dimension for that matter. And so the idea that there was just one geometry basically completely splintered, and we realized that there are these diversity of different geometrical concepts, and that's what I view as happening in set theory now, and has been for some time. There isn't just one concept of set. We have many different concepts of set, and these are described by basically the different combinations of axioms that we can show are consistent using forcing and so on, and not only forcing, but any of the methods. So we have lots of different set theoretic worlds that we might inhabit in the same way that a geometer can inhabit different geometrical worlds. And it's interesting for the geometer to sometimes look at hyperbolic space and sometimes look at Euclidean space, and to compare the different geometrical truths in these, and that's an interesting mathematical activity. And similarly, it's interesting for a set theorist to jump from world to world and to compare the different nature of set theoretic truth, and therefore often of mathematical truth in these different set theoretic worlds. It's really quite a fascinating development.
Right. And I think my last question would be of a different flavor, but it still deals with the Gödel's incompleteness theorems. You have some physicists and mathematicians which discuss it in the context of consciousness. So you have Roger Penrose, which famously says that Gödel's incompleteness theorem serves as an argument to which the mathematical mind cannot be fully exhausted by computation and algorithmic processes. On the other hand, you have people like Douglas Hofstadter, who uses Gödel's incompleteness theorems in order to illuminate how consciousness works as a strange loop, as what he calls it. Do you think that Gödel's incompleteness theorems have anything to say about the human mind and consciousness in general, not necessarily according to their views?
Right. There's there's dozens of these kind of applications of the kind that you mentioned. I mean, those are maybe some of the more prominent ones, but there's all kinds of arguments and applications of incompleteness and so on that one can find in pop culture, and often I'm quite skeptical of those kind of uses of the incompleteness theorem. I mean, the Gödel incompleteness theorem is a very specific theorem talking, if you have a certain kind of theory that has an algorithmic procedure to enumerate its axioms, then it's going to be incomplete. And so it's a very specific mathematical claim, and I don't see it as so much connected with these applications to human consciousness. For example, in the case of the Penrose argument, I mean, part of the argument is that, well, okay, so the consistency claim, the theory doesn't prove its own consistency, but we can see that the theory is consistent. And I don't think that's true, that we always can. I mean, if you start with the piano axioms, and then sure, you can add the consistency assertion and the consistency assertion of that, and the consistency assertion of that, and so on, and you can iterate this for quite a long way. And you can even start climbing into the recursive ordinals by describing the process by which you're iterating. And so what you end up with after having climbed up this hierarchy quite a bit is a theory that's saying, well, the process of adding consistency assertions according to the relation defined by this process is still consistent. And my view is that, well, once you get up very high in that hierarchy, then we're not really able to see that the theory is consistent, because maybe we've made a mistake with our understanding of that relation, and we should have some doubt. And what we should learn from the incompleteness theorem is that, well, when you have a stronger theory, in its stronger inconsistency strength, then you have to be a little less confident in the consistency of that theory. And as you move up to these stronger theories, you have to lower your confidence in the consistency of those theories. And so it's not a kind of perfect knowledge situation, which is what the Penrose argument really requires us to actually know for a fact that the theory is consistent. And that's something that we can't really know. And this is just becomes completely clear once you start climbing very high in the consistency hierarchy, which is what the large cardinal hierarchy really is all about. So we have the axiom of set theory, and inaccessible cardinals are a step up, a very high step up in consistency strength, and then hyper inaccessible and malo cardinals and measurable cardinals and strong cardinals and super strong cardinals and super compact cardinals and so on. As you go up in these infinity notions in set theory, it's also going up in consistency strength. And we just don't know if they're consistent or not. Many set theorists think that the smaller ones are definitely consistent, but they're a little less sure as you go up. And this is, of course, the only rational attitude to take, is that as you go up in the hierarchy, you have to just be less sure of consistency. And,
Yeah, sure, but
go ahead.
But what if you have someone who denies the reality of those very high cardinal numbers? I mean, fine, those are some mathematical fantasies, but truthfully, we're only concerned with, say, we are Brouwer, the famous intuitionist. We're really concerned with this fragment. And when we deal with this fragment, we see that it's consistent. So yeah, perhaps I'm not sure about the consistency of very weird mathematical systems which climb up strange hierarchies, which nobody can really envisage how they would look like. But do you think they can take off the ground the proponents of the Penrose style arguments if they restrict themselves to the sort of real part of mathematics?
No, I mean, the essence of my argument, you're just saying, well, I'm not up there, I'm down here, but it's really the same phenomenon. The point is that the Penrose argument relies on us knowing that the theory is consistent and always being able to do that. And it doesn't matter to me whether you're talking about in the Brouwer level or in the large cardinal level. This is just a different place, but the phenomenon is the same. It's still the same consistency hierarchy, and we can't really be sure of consistency as you go up, even at the Brouwer level, or at the intuitionistic level. I mean, at these sort of very weak arithmetics and so on, we can't really be sure. As you go up, we should be less sure that the stronger, say, the theories that are used in reverse mathematics, we should be less confident in the higher theories than we are in the lower theories. I mean, we can be very confident of all of them, but it should be graded because the consistency strength is going up, and so we should be slightly less confident each time.
I think we should stop here.
Okay.
Thank you for joining me. So yeah, thanks.
Well, thank you very much. It was a pleasure to talk to you.